Let's examine one of the simplest and one of the most important RC circuits. Here I have a resistor connected to a capacitor with the bottom plate of the capacitor grounded. Over here I have a switch I'll call SW, and initially this switch is in the position that the resistor is connected to ground. At some point in time I'm going to change the switch position and switch it to the battery voltage, and we'll explore what happens with this circuit. But let me mention something. It's very interesting that if you take resistance and you multiply it times capacitance, you get time. In fact, the resistance of this circuit times the capacitance of this circuit is called the time constant. And this is a certain amount of fixed time. The resistance is constant, the capacitance is constant. We end up with a fixed time constant. So let's examine what happens when I change the switch position to the battery voltage. Let's call the voltage at this part of the resistor, call it VI for Vin. The voltage at the top plate of the capacitor, let's call that VO for Vout. So let's examine what happens to the output voltage when I change the switch position. Let's plot voltage versus time. So here we have volts, and here we have time. So initially, before I throw the switch, the Vin, or the Vi, is at 0. Let me change colors. So initially Vin is at 0. I throw the switch, and Vin changes abruptly to the battery voltage, and it remains at the battery voltage continuously. Let's examine what happens to the output voltage, VO. So we know that a capacitor resists change in voltage. So at the instant I throw the switch, the capacitor is going to remain at 0 volts. And the capacitor is going to charge up slowly. And it'll approach the Vn rather slowly. Let's examine what's happening. Initially, when I throw the switch, the predominant voltage drop is across the resistor, and very small voltage drop is across the capacitor. So at this time, as soon as I throw the switch, the maximum current is flowing in the resistor, but the capacitor is charging up. So at a later time, I'm going to have more voltage on the capacitor, and I'll have less voltage in the resistor. Let's say this is the voltage on the capacitor. So because I have less voltage across the resistor, the current in the resistor is going to be less. And the current in the resistor becomes less and less, and it causes a slope change. Initially, the slope change of Vout, the slope is very high at the origin, and as the resistor current is decreasing, the slope on this charging curve is decreased. Now, if we say that this unit of time, we can call this RC. So one time constant is this amount. This time over here would be another time constant, RC. And again, if we take another chunk of time here, this would be another RC. So this circuit here at this point is charged up 3 time constants. At this point has charged up 2 time constants. At this point has charged up 1 time constant. We can write an equation for this V out versus V in. This is V out, this is V in, or VI. It turns out that the equation for the output voltage, V out, is equal to the input voltage, VI, times 1 minus e to the minus t for time divided by the RC time constant, RC, close bracket. Now e is a natural logarithm. E is equal to 2.7182, so on and so on. So E is a constant. Again, T is time, RC is time constant, and VI is Vn. So let's look at this equation. For example, at T0, what does it tell us? At T0, we know that the exponent is raised to the 0 power, which is equal to 1. So this second term becomes 1. 1 minus 1 is 0. So 0 times Vn gives us a V out of 0. So at time t equals 0, this equation seems to work. As the time becomes very, very long, this E term becomes 0. It approaches 0, and so the output voltage in that case approaches VI. So that seems to work. So if we look at T0 and T very long, this equation seems to work. So let's examine a certain point in time for this curve. Let's say that we give it an input voltage, VI. VI stays constant. And the output, V out, starts charging up. So on, etc. Let's find a point where the output is half the input voltage. Let's find the point right here. Now this is a useful point for a lot of different circuit designs. So let's see if we can find that point in the curve. Now, when the output voltage is equal to 1/2 the input voltage, this term here will be 0.5. 1 minus 0.5 is a half, times Vn gives us a V out of a half. So if we set this E minus T divided by RC equal to 0.5, and we solve for T, we can find out this time here, T, as a function of the time constant RC. So if we take the natural log of each side, and I'll take the natural log of this, I get minus T equals the minus T divided by RC is equal to the ln of 0.5. So let's see, time is equal to minus RC ln of 0.5. So if I take the natural log of 0.5, that comes out minus 0.69 3, and minus times the minus gives us a plus, so this is RC. So the time to get halfway up the waveform is 0.693 times RC, which is a useful value to remember. Let's review our findings. If we have a resistor and a capacitor, we ground the capacitor, we apply an input voltage. Say it goes from 0 to some voltage, we just call it 1 volt, 0 volts. We know that R times C is equal to time, or RC is in units of time. So if we have a resistor of 1 ohm times a capacitance of 1 farad, we get 1 second of time. If we change the units, instead of ohms, if we use k ohms, and instead of farads, we use picofarads, we get a different unit of time. We get nanoseconds. And a nanosecond is a very small unit of time. It's like 10 to the minus 9 power seconds. So light travels approximately a foot in a nanosecond, and light travels very, very fast. So to summarize, we know that the output response will do something like this. It'll charge and approach a final value. And we know that at the halfway point, that has taken 0.693 time constants. If we plot time constants on this axis, say this is RC to this point, we'll take another RC time constant to this point. Let's take a third RC time constant to this point. It turns out that at 3 time constants at this point in the curve is still not fully charged. It's at about 95% of the final charge. At 2 time constants, we are at about 86.5% of the full charge. At 1 time constant, we are at this point, and that's about 63.2% of the final value. And we'll explore what happens with this circuit. But let me mention something. It's very interesting that if you take resistance and you multiply it times capacitance, you get time. Over here I have a switch I'll call SW, and initially this switch is in the position that the resistor is connected to ground. At some point in time, I'm going to change the switch position and switch it to the battery voltage. Let's examine one of the simplest and one of the most important RC circuits. Here I have a resistor connected to a capacitor with the bottom plate of the capacitor grounded. In fact, the resistance of this circuit times the capacitance of this circuit is called the time constant. And this is a certain amount of fixed time. The resistance is constant, the capacitance is constant. We end up with a fixed time constant. So let's